Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my great pleasure to introduce Felix Hill from the Cambridge Computer Lab. Felix is currently finishing up his PhD there, and he's done some fascinating work on using deep neural nets to teach machines to understand human language. The floor is yours.
And thanks, Katia, for introducing me, and thanks for coming. I think there was possibly a talk advertised with a different name, so all of what was in that previous abstract will be in this talk. I just changed the framing of the talk a little bit, so it's not the case that I'm going to talk about something completely different. So I work on automatic language understanding, and it's a really hard problem. There are lots of things in artificial intelligence that are hard, but this is one. This is, I guess, Siri, and you can see that it's not perfect yet. So there's lots of things in the language there that the system hasn't really understood. So there's a kind of semantic thing which is internal to the words. Alcohol poisoning is very different from alcohol. So just the addition of the extra word radically changes the meaning of that chunk, which seems to have confused it. It doesn't seem to have a good sense of the intention of the user or the severity of the situation. And these are all things which humans are kind of innately aware of when they, or maybe not innately, but they're intuitively aware of when they interpret language, when they interact with people. So, and then, machine translation is another application where, you could think of it as an application where we need to understand the meaning of language. Between languages that are not very close, or for which there's not a lot of data, it's really still quite bad. And even between, it's not a well-defined problem. Often there's not one single correct translation. But even between close languages, you can't use it for things like translating a road sign or something, because there's a good chance that what you get wouldn't be correct. So I think that one of the big factors behind, it's not a limiting factor because it's quite hard to do something about it, but one of the factors behind why these automatic systems lag behind human-level performance in interacting with language is a clear difference between the way in which these systems are trained and the scenario in which a human acquires and learns language. So a lot of my work so far has been sort of inspired by the idea of bridging this gap, making these two things a bit closer, but I haven't done a lot yet, so I'll talk about that, but there's much more to do and much more radical way in which we can make language understanding systems like human language learning, and which I think will hopefully lead to systems which give more human-like linguistic behavior. So typically at the moment, most language understanding systems are still trained in a classical sort of machine learning, supervised learning way. So the idea is to approximate a function between the inputs and outputs in some fixed set of training data, which is sort of usually defined before the training starts. And then, the kind of objective of these models is to reduce the mathematical cost function, which is maybe not quite like a single cost function, maybe not quite like what humans are doing when they're learning. As I said, the training data is fixed beforehand normally. People play around with how you order it and things like that, but it doesn't tend to depend on what the model already knows. And often with language, it's unimodal, so often it's text or linguistic resources. So if you haven't seen any sort of examples of this, I'll talk about some in this talk. Whereas human language learning is a bit different. So it's generally, we do get some instruction as children about language, but it seems like the vast majority of what we pick up from interacting with people and hearing correct examples of language without any sense of knowing what's wrong necessarily. There's clear sort of strong motivations and urges that seem to be guiding human language learning. So usually we want to learn how to say something in order to do something. So that's not really well reflected necessarily in the current training setting. And as I said, it's very much the case that if a child sort of wants to know more about something, then by the time learning has progressed a little bit, he's able to sort of move the interactions, the conversations, or whatever else he's doing in a direction that will help him to learn more about that. So it's kind of guided by what the model already knows in a way, which is not the case with a lot of the current supervised models. And yeah, it's also totally grounded and embodied, and the child is, so learning the meaning of a word might be something like learning what a concept looks like and what it maybe how it is physically, and then attaching a word label to that, something like that. Whereas if you have these models trained on text, then learning the meaning of a word is something it's not quite like that. So yeah, so there are some quite obvious discrepancies there, and I think that there's good reasons to try and bring them to reduce this discrepancy. It's obviously not a priori true that if we do that, technology will improve, but there is quite a lot of evidence that happens, at least to some degree. So I think it's a good thing to try. So yeah, here are some sort of buzzwords, but I like to think of it as kind of two ways of understanding psychology. Or so there was kind of cognitivists who were really focused on how the brain works, and then behaviorists who were kind of very much trying to model human behavior from inputs and outputs, and a sort of much higher level understanding of behavior. And I think what would be nice is if we can kind of bring these two processes together when thinking about language understanding models and language technology. And a lot of the current work has been focused on the top part, which is nice, but I feel like, especially for language, which is such a behavioural thing, we're missing out on a sort of level of modelling which could be really useful. So, having said that, there is a small amount of work which treats language like this, but then that work hasn't necessarily embraced all the options and the possibilities that the latest work in the sort of function approximation, the cognition part, can offer. So, yeah, I think if we do that, if we combine these two paradigms, and I think it's becoming more and more tractable to have, principled cognitive models, principled models, but also trained in a scenario where where the model learning in the setting there is much more like a much more realistic setting of human language learning. So I think, if we do that, there's good evidence that we can. Obviously, we should be able to get much richer scientific insights just because it's a much more realistic model, right? So it's a closer model. So anything that we learn from the model should be slightly more valid. But also, there's a bit of evidence in what I'm going to talk about, and there's other pieces of evidence that by making the training setting a little bit more like it is for humans, we will also improve the performance. We'll get more human-like output. We'll get systems which people can relate to more easily. So. And I've called it sort of, the idea is to turn models of language understanding into agents of language use. At the moment they really are these kind of very isolated models separate from the overall human problem of language as a sort of tool, as a way of interacting, and it would be nice to bring these models into that world. Having said that, it's a really ambitious program. It's also not particularly novel. I'm sure lots of people have thought about this in the past. I think that at the moment there's a really good chance that now seems like a really good time when this might be more tractable because of the data that we have, and also the computational resources that are available now. So I've thought a bit about trying to do this, but actually most of my work has been in the first part of this problem, and just a little bit extending towards trying to get towards sort of situated, interactive, or goal-driven learning as well, but while including that function approximation part. So that's what I've done to date. It's nowhere near being what I'd like to do in the future. So one way in which I did this, and one way in which I thought about, so I used a lot of. Katya said I did some deep learning, and that's true. But I think, especially with language understanding, the particular nature of the model isn't so important. But what does seem to be quite important is the sort of the fact that deep neural networks encode words or other things which carry some meaning in these sort of distributed representations. So a lot of other, prior to this, language understanding systems often would encode a word just as a sort of, as a symbol, as an atomic unit, and then maybe features would be the presence or absence of a word, or and you can get a long way with that. So even now, if you want to know which documents have the same content, things like TF-IDF is incredibly powerful, and this is just a thing where you sort of basically count how many words are overlapping and count their frequency. But in the sort of the neural language models which have emerged more recently, word concepts are represented in vector space. And so a lot of the work I was doing was trying to understand these representations of words or phrases or sentences. And the reason being that if you want to sort of put any knowledge as well, if you want to sort of adapt these systems to put knowledge into them, then it can be a good way. You see, it can be a good way of transferring knowledge from one training regime to another training regime. Often these representations can be trained with quite task agnostic objectives. It might be just trained on some text or on some other naturally occurring things, and they can acquire some principles of language which are then useful to inject or to add to some other system. So that's why I was interested in these sorts of representations, and they sort of play a part in all of the work that I've done. So lots of people had developed ways to learn such representations for words, and there is a whole history going back 30 or 40 years of different ways to acquire, usually from just raw text, these sort of dense vector representations for words, which they exist in some space, which then itself corresponds to, often corresponds to human intuitions about what words mean. So words that have a similar meaning cluster into one place, and things like that. Now, one thing that people hadn't done is thought about, or there hadn't been a lot of work on extending this to representations of phrases or larger linguistic chunks. And as more and more neural language models emerged which were able to be trained on larger data sets, it became obvious that there was ways in which these models represent phrases and sentences. And so one piece of work that I did was about understanding the internal representations of these models and how well they correspond to human understanding, and also the extent to which they can be useful for applications. So this is a sequence-to-sequence model. It's an RNN, which in some sense reads a sentence in the source language and then generates word-by-word sentence in the target language. But there's a bottleneck in the middle, which is where the model stores the information corresponding to what it's read in the source language and conditioned on which the model generates or starts to generate the words in the language. And then, of course, generated one word, the generation of the next word is conditional upon the word it's previously generated, as well as this prior information. So when I first saw this, I thought, this is magic. It must, in that representation in the middle, the model must remember everything that there is to know about the input sentence in order to be able to sort of get a plausible reconstruction of it. And so I thought that this sentence representation must be like a real, a really kind of high fidelity, clear representation of what this sentence means. But so this is when I started to become quite interested in understanding these sentence representations. In actual fact, it turns out that that's not the case, that the representation there is very specific to the translation objective. So in particular, it's actually strongly biased towards the meaning at the start of the sentence. I guess the reason that, intuitively, and I'm not 100% sure, but what feels like the reason for that is that the task of starting to generate the target sentence is the most critical. And once it's generated a few words, it's kind of got its language model, it's got its sense of what might come next based on the words it's already generated. So at that point, the knowledge in the knowledge in the weights of the generating RNN can start to do something. It can start to, in there it can encode its language model for French. But what it really needs to do is get the first words right. So it seems like that's the most critical part. And so what that means is that these, if you start, this is a very short sentence, but if you look at the way these representations are for much longer sentences, they seem to encode information about the first chunk of the sentence and then be less and less influenced by the later words. And actually that's kind of confirmed by the fact that I think people actually got a performance improvement in these models when they literally swapped the order of the English sentence and just retrained the model. So yeah, you can do that because this model doesn't have any knowledge of language before it starts training. So the fact that it's being trained on backwards English is not a problem for the model. That wouldn't be a realistic strategy in the long term, I think, because what we'd like to do is have these models learning from monolingual text, learning general principles of language, but also then doing the translation objective. And in that case, the model would know that the English is backwards, and so it wouldn't have a good sense of that. So then I started playing around with similar models, but just to try to understand maybe can we get richer sentence representations, richer ways of encoding sentences in the So one objective we worked with was this. It was kind of inspired by the idea of denoising autoencoders, which is a sort of representation learning technique, which was usually used for images. So this was like you blur the image a little bit, and then you get you train the model to reconstruct the image without any blurring. So usually it's just a small amount of random noise. But in this case, it was even more crude than that. It was literally just a small mistake in the sentence, and we trained the model to reconstruct the sentence without that error. And we had a couple of ways to do that. So one would be just sort of random swapping of pairs of words, and then another thing would be just random deletion of a word. And as I'll show in the results, these sorts of representations have other properties which are useful. So this is particularly useful for a paraphrase, for sort of using its prior information in a paraphrasing system. It seems to be quite good at that. So paraphrasing is the idea of detecting when two sentences have roughly the same meaning, but they might be written in a different way. So yeah, we didn't experiment for weeks and weeks with the possibilities with such a model, but of course you can play with this noise function. You can increase or decrease the number. And actually what did seem to make quite a lot of difference to the optimization was the curriculum. So if you slowly increase the amount of noise here, then the cost of the model, behaves nicely. It goes lower overall.
Encouraging the encoding in the middle to be much more like a high fidelity copy of the text, because you are penalizing it if it means the same thing, but use different words.
You're penalizing it if it means the same.
You're trying to get it to construct the exact same sentence, not the sentence with the same meaning.
Right, yeah.
So did you look at that?
So it would be, what would be ideal is if, you could have, the obvious thing to do in a kind of not particularly creative way would be if you had a huge bank of sentences which had equivalent meanings, but were written differently, then you could train such a model, and that would obviously, I think, be a good paraphrasing model. And in fact, when I use this system in a supervised task, so when I use this system in to sort of use it as prior knowledge for a paraphrasing system, then that's exactly what happens. So we put a classifier on top which is trained on some paraphrasing data, exactly like that. But the reason that we can't do, or we aim, the reason that I didn't try a model like that from scratch is that there is only a small amount of such data, so it's actually not trivial to get sentences whose meaning is equivalent. But so there are data sets available, but of course, there are many possibilities for sentences of equivalent meaning and things like that, and it's actually not trivial to get really nice data. So in all of these experiments, I focused on what I sort of roughly called unlabeled data, which is, I defined it as something which wasn't created for the purpose of training models. So instead, it's naturally occurring things. It's not all raw text, but it's naturally occurring things that. In this study, we didn't look at things like paraphrasing data, because generally that has to be kind of curated. There might be nice ways of getting it, but that I didn't know. So, yeah.
Maybe a brief follow-up. Is there a way for you to quantify how high fidelity that hidden representation is that it has learned, or is it mostly end-to-end task performance?
Well, exactly. So I'll come to that basically.
Okay.
Yeah. So I'm just going to sort of introduce a few different models that we compared in this study. So another one was this dictionary representation. So in this work, so there was all these existing methods for training word representations, which are quite well established. So the first thing in this model is to just train, get good high quality representations for a full vocabulary of words, so 200,000 words, something like that. And then the intuition behind this model was, with all these models, if you'd like to get a good representation of a sentence, what we need is a kind of signal which says, well, what does that sentence mean? Or at the very least, some objective function which we can sort of require a model to know about a sentence in order to do something. In this case, the idea is that the meaning of a dictionary definition, or maybe a very small description in an encyclopedia or something, should correspond to the word that definition defines. So if we've got a good quality space of word representations, we can use that as a sort of training signal to train a model to read definitions and arrive at the point where that word is. This actually gave some really nice results, as I'll show later. So this turned into a really interesting model. And of course, so dictionaries are labeled data in the sense that a human was required to create them, but they're nice in the sense that they are freely available in many languages. So this sort of data does exist. And a nice thing here was that it became a really nice test bed for different models and understanding about what the important information is when we encode. So this is a sort of classical RNN. We also tried one with the long short-term memory. So this has some sense of word order because the updating function between one hidden state and the next is not necessarily symmetric. So the order in which the input is put in will affect where the model ends up in the word space at the end. But we also just replaced that with addition. So this is much faster to train. And it's also faster to encode at the end, I guess, at test time. We did that because reviewers asked us to do that as a baseline, but actually it worked really well. And then finally we had another variant, which was that the input to the model is the pre-trained embeddings, which are exactly the same. So the words represented here in yellow are in the exact same space as the word that's the target on which the model is trained. And then there's a mapping here, a nonlinear mapping that's parameterized by some matrix. It's the same matrix in each position, and then they're just added together. We also tried this model, the RNN model, with the pre-trained word embeddings as well as input. And so it became a nice way of, there are a number of ways of evaluating this model. Just by playing around with it, and so just by inputting at test time, inputting arbitrary sentences and then retrieving from the space, we found that it really did seem to have quite a good sense of what these sentences mean. So, and it generalizes quite nicely away from the training data. So, with something like this, a habit that would annoy your boss, that's clearly not in the training data. There's no dictionary that would define a word like that. But as I'll show you, the model comes up with plausible candidates for that. And equally, we found that, slightly strangely, if you train the model on quite a lot of dictionaries, then it kind of knows enough to be good at doing general knowledge crossword questions. So it was actually getting a really high proportion of things from like the Guardian quick crossword correct, especially if you limit the search at the end to words of the length that the clue specifies. So you use the information in the clue. So this, I could show you that this got lots of attention because it's actually not really the motivation behind the model at all. It was just that we were looking for a way to evaluate it other than just on the held out training data. But evaluation on the held out training data was useful in terms of comparing different models. So that was a useful thing. But yeah, as you can see, the candidates here are really quite plausible. And this is true for lots of queries like that. There are many things that it's not good at, and they're also quite insightful. So negation. There are lots of hard problems in sentence processing. Words like negation massively change the meaning, but they're kind of small. So it's obviously very nonlinear, the mapping between form and meaning. And here, yeah, you can see it's got this quite good factual knowledge as well. So this is, I mean, getting question answering factual knowledge into a continuous embedding model is quite difficult because often the factual answers are not very high frequency, and you maybe need what seems like more structured knowledge. And of course, there are many questions that this can't answer. There has to be a certain degree of overlap in the form between here and a dictionary definition. Otherwise, it wouldn't be possible. So if you asked it, who is, what's the name of Barack Obama's eldest daughter? It wouldn't know that. It couldn't generalize that far from the training data. But things that are roughly about dividing properties, it's pretty good at. So I think the message here is that this can be used as a smooth interface maybe, but you would also need a way of combining it with a larger knowledge base, obviously. Other ways of getting sentence representation. So data that does exist is, and that we do have a lot of, is this image caption generation data. So, I mean, this qualified in my definition of being unlabeled because I guess it was these images were originally captioned for making you a nice website or something. So in that sense, it wasn't for the purpose of training a model. This data set, or data sets like this, is a Flickr data set. They've been used for lots of things. So actually, going the other way around is the more interesting bit, which people have done. This is, sequential generation of captions conditioned on the image representation. That's very interesting. We just reversed it so that the pre-trained, so you train a convolutional network on classifying images. And then the idea is that the final layer of that classifier forms an embedded representation which encodes the content, or at least encodes some view of the content of the image. So if you take such a network pre-trained, you can use it to get out relatively interesting, possibly sort of from the visual modality, representations of an image. And then if you consider that to be a fixed representation which isn't updated as this model trains, the rest of the model, then the task is just to read the caption and arrive at a place in the space which corresponds to the meaning of the image. So you could think of this as a sort of visual signal for getting sentence representation. So more visually, it might prioritize things which are obviously concrete, which are clearly exist in the physical world, things like that. Okay, and then as a baseline, surprisingly effective is, or in a lot of evaluations, surprisingly effective way of getting a representation for a phrase or a sentence, and this is what a lot of people have done previously, is just a sort of crude addition or averaging of the words. It's a bit of a weird phenomenon why this works at all. People have discussed it. There's some intuition, especially in this case. So this is one way of getting the word representation. So you store a set of embeddings for, you can think of them as input words, and then a set of embeddings, a different set of embeddings for the same vocabulary as output words. And then this model, the SIBO model, essentially takes the input embeddings. So in a training case, it acquires these training cases from text. In this case, 5 consecutive words. The 2 outer words of the 5, in both directions, are added, or the input representations for those words are added to get a single input representation. And then that's used to make a prediction, and the model is optimized so that the highest scoring word in that case would correspond to A as the output word. So in the objective function here, there is some incentivization for these things to be additive in some way. So you would want the words to add up and have some sort of coherent meaning from which we can make a prediction about the word in the middle. So it's just a small intuition as to why you can add these and still get something plausible. So we changed this model in order to kind of make it better at really getting, or designed it to hopefully be better at getting a type of sentence representation. So it's a very simple change to this SIBO model, in fact. All it does is the input representations in this model are taken from one sentence, and then the output representations are taken from sentences which are either side of it in a book. So the signal that the model is trying to exploit is something to do with the narrative that connects one sentence to the next sentence in a book. So you can imagine thinking like, well, what sort of knowledge would I need? What sort of representation would I need in order to make a strong prediction about the word, about what's in, or about what came before and what came after? But this model is also designed to be kind of super simple in the sense that we had lots of evidence that just adding things and things that weren't aware of word order are actually quite effective in representation. So this model, we thought about doing it with RNNs and those sorts of things, but we found that we could get this model working really quickly with this quite simple strategy. So all we do is we initialize random word embeddings corresponding to input words, which is the words in the middle of the sentence. Then they are simply added to create what we think of as a sort of core sentence representation for the middle sentence. And then based on that, in exactly the same way as in the SIBO model, so using a softmax, we make predictions, and we just try and optimize the model to give high scores to all of the words in the sentence before and the sentence after. These words have no status relative to each other, so they are all equal. It's just predicting, it's all bag of words, it's just predicting words in nearby sentences.
And the embeddings of each word shared.
So embeddings that are in yellow are not the same as embeddings that are in grey. So that's an interesting design decision, which was also made in these models, and it was shown that with experimentation that this was actually necessary. So it's quite interesting to think about why you would want that. I think you would obviously always have a high score predicting yourself, but you don't necessarily want that in language. So you don't want the target embedding of a word to necessarily be the same as the input embedding of a word, because these are sort of, the yellow words sort of need to be good at making a prediction for what words come near to those words, and often that is not the same word. So that's a little bit of intuition, but I'm not 100% sure. I haven't sort of tried to demonstrate it formally. So in this case, you can think of these representations as being slightly different to these ones because they're optimized to be added. So you need to add them up and still get something which makes sense. In the sense that the representation in the middle needs to be good and useful for predicting the content of nearby sentences. So how is this different to other models? Well, I've got a little demo, because it turns out that this is actually quite nice. What you end up with is representations which can be added, and you get slightly more plausible representation at the end of it than what you would have done if you just trained them using the skipgram or the SIBO model. So in this demo, all I did was I trained such a model, and I trained a SIBO model, and then I encoded something like 2 million sentences from bad literature. So the literature was freely available because it wasn't published, and I think, it wasn't published because it doesn't seem to be very good. So what you can do is just enter any sentence and then retrieve from the space the nearest sentence in the book. And you can see that there's some quite nice contrast between doing this with the old SIBO model and doing this with this new model, which is optimized to be slightly better at sentence representations. So it's a little slow because it has to do quite a... Okay. Yeah. So, I mean, neither of these is flawless. The model can't do anything particularly clever. It just has to retrieve from a set of sentences which already exist. But you can see that on the right, it seems like what it's producing there is more similar to the query than what it's producing on the left. And it's possible to try this with any sentences and get a sense of the principles that the representation's encoding. And one thing that struck me here, it's not It's certainly not there at the moment, but these representations, in order to make this sort of fit on my server, I had to make these quite small. So they're both 100-dimensional, the SIBO and the FastSent. And it struck me that you can encode quite a lot in 100 dimensions in these representations. And I thought, if we can get a little bit better at this, then it opens up the potential for a sort of top-down generation. Because what's nice about the sentences on the right is that they are grammatically correct. They're perfect English, and the reason being that they've written by someone. What's not nice is that they maybe don't have exactly the right semantics. But equally with current language generation, you may well be able to train a model to get really good semantics, but then it might also make some linguistic mistakes which aren't very natural. So there could be advantages or ways of incorporating this into a generation system such that you produce something which has already been produced before and is therefore guaranteed to be correct English. And because it's in this embedding space, it's already sort of readily available for use in a neural language model, which is not the case with maybe other approaches to information retrieval which existed before. So that's another potential use. And yeah, we can try one more sentence just to try and give the... So another nice thing about this model is that there is no model in the sense that it's just all in the word representation. So there is no... The encoder is just to add them up. They're just optimized word representations which are slightly better at adding. So yeah, I mean, it's not clear exactly what this demonstrates, but I think, well, to me it demonstrates that, yeah, there's a more plausible sentence meaning space on the right-hand side than there is on the left-hand side, but these sentences on the right are undoubtedly slightly closer than what's on the left. Okay. So yeah, so I compared lots of models to try and understand their representations, and there is some interesting differences between them. So some of these models are aware of word order. They have within their capacity, they will encode something different depending on the order in which you input the words. Others are completely blind to word order. And then they obviously require different levels of training data. So the nice thing about trying to get these representations is it's kind of a sort of a rudimentary unsupervised learning. You use them to hopefully acquire knowledge, which then you can add to some other system with a specific task. And so, but the degree to which they are unsupervised is not equal. So some of them really can be trained on just an unordered list of phrases and sentences. Others, the ones that rely on the narrative structure of one sentence to the next, then those sentences must be ordered. So the last model that we discussed, there needs to be it needs to be trained on a book in which the sentences have order. Otherwise, of course, the objective of predicting words in nearby sentences doesn't make sense. And finally, some of them rely on a more structured resource, such as image captions or dictionaries. But these are all things which exist in the world without necessarily needing to be curated. So this is Katya's question. How do we evaluate this? So people are there's lots and lots of work in language processing on representation learning, and it's quite fun and cool. But they're still only just starting to understand what the possible applications of this are. So one way that people typically evaluated word representations was just to see how closely the space of word representations corresponded to some measure of what's in people's minds. So by doing that, they'll ask people what words, or they'll get some sense of what words are similar, or maybe they'll even use brain imaging data to understand how similar representations are in the human mind, and then they'll compare a simple metric like dot product or Euclidean distance or something like that. So no training data, they'll just query the representation space and see how close they are. So that tells you, well, this is maybe a nice model of cognition, but it doesn't necessarily guarantee that the representations are useful for anything. On the other hand, there's these what I called supervised evaluations. So that's not to be confused with the models being supervised. The models in general are kind of unsupervised, the ones that acquire these representations. But when we evaluate them, one thing you can do is take some extra training data, use them as features in a classifier. And the idea being that the classifier is kind of neutral in the sense that it's not particularly, so this was logistic regression. And then if one representation allows this classification problem to be resolved better than another representation, the feeling is that there's more useful information in that representation. So I mean, neither of these is perfect as a way of evaluating for various reasons, but I tried to use both just to, that was the sort of compromise. So what we found is that, yeah, I mean, one interesting thing was that when you use the representations in the supervised setting, you get radically different results of what's better than when you use the representations in the unsupervised setting. So generally speaking, the simpler models, the shallower models, the models that don't encode word order, they perform better on these unsupervised evaluations. Whereas in the supervised evaluations, it's the more complex models with a recurrent neural network or some word order encoding. Now, yeah?
Did you try other simple evaluation methods like k-nearest neighbors or something that's nonlinear but still simple?
So how would you evaluate using k-nearest?
So embed if you're trying to do some supervised task, I guess the movie recommendations is like, how many stars do you give it?
Okay.
So find the nearest sentence in your data set based on some sort of distance in the embedding space, and then give the sort of the k-nearest neighbors classification.
Yeah, that's true. So that would be kind of along the lines of what I've called the unsupervised evaluations, but using the other, using a slightly different data set, which isn't this sort of psychological measure, but rather some other measure of like what's correct, like a listing of.
I would call it the supervised evaluation, just with something that's not a linear classifier.
Okay. Okay, so you're actually using the training data,
yeah,
but the classifier is nonlinear. Yeah, I'd say the reason that I used the exact formalism that I did was that other work had already used it, so we could just do a direct comparison. But yeah, you're right. I think that ultimately the test of any of these representations should be, how many different systems can I put them into in order to gain some improvement. The problem is that it becomes a bit untractable, at least for a piece of work like this, where we're comparing many, many different models. It became a bit intractable. Ideally we would sort of apply the representations to many different downstream applications and then evaluate how well they perform. So if we allow nonlinear classifiers here, then it kind of just would open up a huge sort of scope for comparison in many different models. But yeah, that would be the most realistic thing to do, because presumably it would be a sort of state-of-the-art model in which it was used. It wouldn't necessarily be. And of course, there's a nonlinear element to the decoding process for a lot of these representations. So the cost is computed based on the words that are generated conditioned on these representations in an RNN, in the case of these models. And so it maybe isn't surprising that they're not, as you kind of suggested, it maybe isn't surprising that they're not very good at the unsupervised evaluation. And you could argue that maybe even in this case, it's not surprising. It might be that you need a nonlinear classifier in order to get out the full potential of these representations. But it's a trade-off, because if you allow the classifier to be too powerful, then you may be not isolating the effect of the representation. So it could be that the classifier would work with, it's just exploiting the training data, the little bit of training data you add on top, maybe, or something like that. So I think that was the thinking behind defining a framework in which you use a very simple classifier to evaluate these things. And so by following the framework of other authors, I was able to at least compare my representations with theirs and sort of build on their work rather than redoing it. So, so there were some, this is a sort of kind of ugly table of results, but there were some interesting insights. So on the supervised evaluations, it's actually the case that the dictionary training really does work quite well. And the model with pre-trained embeddings, in most cases, so these are different examples of the classifier thing, right? So they correspond to different tasks: movie recommendation, subjectivity analysis, and things like that. So on the larger number of those, the best performing model is the bag of words dictionary representation model, the one with the pre-trained word embedding. So this is quite interesting because it's an example of a little bit of transfer learning. So this model is learning about word meanings first from raw text, and then kind of applying that knowledge, leveraging the dictionary definition data to learn how to combine those meanings. And then based on that, you get quite a rich phrase or sentence representation. And the denoising autoencoder model seems to learn features which are useful for paraphrasing. So this is quite a high score on the Microsoft research paraphrasing data. So that, yeah, this is a reasonably sized data set. So there are some people who have just trained a model, the similar sort of model directly on that data. But I wanted to, in this work, to sort of understand what could be learned from this unsupervised pre-training acquisition of features. And it turns out that the features are pretty good. They're quite good, the ones you learn with the denoising autoencoder. This is the one where you corrupt the input and then try and recreate the correct sentence.
How does that compare to state-of-the-art on these things?
I think state-of-the-art on MSRP now is about 81 in the first number.
Okay.
So it's
just on that, just trained only on that data.
Yeah, exactly. And that's a model which was trained using the training data, but it was obviously a model which was tailored specifically to that task. And so we're getting pretty close just by using this background knowledge. Having said that, of course, something like SIBO is also, it's the worst model here, but it's also doing okay. So you get quite a lot just from the training data in the supervised evaluation. And then in the unsupervised evaluations, we see quite a difference. So the best performing one here, well, one thing that's interesting is that still adding up word representations actually performs really quite well. So one of the messages from, one of the takeaways from all of this is if we're going to persist with representation learning, we probably need better ways to evaluate. I don't think that these unsupervised evaluations really necessarily get the essence of what we want from a sentence representation. If you're able to just add up the meanings of words in a model like that and get such high scores, I think it suggests that the examples are not. So these typically, unfortunately, this STS and the SIC, it's two separate evaluations, but they both consist of pairs of sentences which are rated by humans for how similar they are. But actually, the inter-annotator agreement on that is very low. It's a hugely ill-defined thing. So you can do that for words, and generally you get quite high agreement. So that suggests that there is a thing there that is relatively common from person to person. But when you do it with sentences, it just totally depends on how the person chooses to perceive each sentence. And so this is a very noisy analysis. It's the best we can do with the current evaluations, but it's important not to read too much into it. One thing that was interesting was that on the test set, which corresponded to images, the model trained on captions was actually the best. So there's a slight effect of modality there. This model is actually better than other models at knowing how similar caption descriptions are, ones that it wasn't trained on. So that shows you that they're actually a little bit specialized to a particular type of language. And then the fast sentence model, which is the one where we looked at the demo, this is actually pretty robust. But again, it doesn't. Looking at the demo, it was clear that this is stronger than SIBO or skipgram. But in these evaluations, the difference doesn't show up too much. So, for me, it says that the evaluations are a bit suboptimal. But one thing that's interesting is that the dictionary representation model, which was the one with the pre-trained embeddings and then trained on dictionary definitions, this actually performs reasonably well in both supervised and unsupervised evaluations. So, to the extent to which this sort of analysis is useful, the conclusion is probably that these are the best representations. Of course, in a perfect world, I think what we would have is a predefined set of downstream applications where we could plug these representations in and measure the improvement or lack thereof, and then plug all different representations in. That would be the perfect evaluation framework, but it hasn't been defined. So at the moment, researchers have to focus on what they can easily compare with other work. So one thing that I've done recently, and I was trying to I thought was maybe a more satisfactory way of understanding representations. This is a memory network. So this is a slightly deeper network in which you can encode, so representations of what are considered to be memories have a slightly different status in this model. So we actually set this up on what we call the children's book task, which is the idea of, it's a language modeling task. So language modeling is just predicting missing words in a sentence, but this model, in the training data, you get access to the previous 20 sentences, and then in the 21st sentence, a word is missing, and you have to predict that word. So it's different from previous language modeling data sets, because normally you just get a sentence and you have to predict the word. And because this is taken from books, there's quite a lot of narrative, which means that things reoccur. And so the model is kind of tested in its ability to look back further than the current sentence and do something sensible. And the baseline for this would be something like an RNN language model. So you literally train the model to just ignore sentence boundaries and train the model to be optimal at predicting the next word. And then at test time, in this case, burn it in with all of that, get to here, and then make a prediction. And you can condition it on the remaining words. You can make your selection based on the highest probability right to the end of the sentence. So that's a baseline, and we compared with that. The memory network has a slightly different architecture. So it does that basically at this level, but then at the same time, it computes a representation of the context and a mechanism which weights where to look at in that representation. And then it recruits that information and uses it to make a prediction. So it's kind of deeper. There's a bit more to optimize, because it has to optimize this RNN which reads the question, but it also has to optimize a network which represents this, and it has to optimize a mechanism which looks at that. So it's kind of three things to optimize. But in the context of representation learning, it's quite nice because you can actually make quite structured choices about how to represent this information. Keep the same softmax attention mechanism, which is literally just a weighted average of which thing in the memory should I look at more than other things. And the representation you choose, the representation form you choose here, can make quite a big difference to the performance of the model. So this is quite nice in terms of understanding representations, because it's a more downstream application. This is not a tool. I mean, most people don't need an application which predicts the next word, but it's closer to an actual language application. So you can imagine this sort of language model is very useful to put on top of a machine translation system to score the outputs. It's useful for any sort of dialogue system to make sure that what's coming out is plausible language. So language models are undeniably useful, and this is a more extrinsic task. It's easier to explain this task rather than getting people to rate sentences or something like that. And we actually got humans to do this test as well, and that's quite interesting because so there is, by the way, I forgot to mention that there's a list of possible answers here. So we got humans to do it when they only had the final sentence, and then we got humans to do it when they had the 20 sentences before. It's actually incredibly boring to do this because it's quite a lot to read in each case. But it's interesting, they score something like 65% correct when they just get the sentence, and that goes up to about 80 when they get the whole thing. And then models they also show that, our models also show that effect, but they're obviously not at human performance.
So did you say you're giving them a list of options?
Yeah. So there's candidates here.
So where are those options coming from?
They're actually always from here. Yeah, and that is. There's a number of things which sort of affect what models work on this. So we didn't actually use the candidates for training. When we trained this model, we just used the knowledge of what the correct answer is. But you could imagine a sort of ranking-based training which penalizes other candidates and increases the correct candidate or something like that, maybe. But in this case, it was just maximum likelihood training, where we just increased the sort of probability of getting the correct answer. So we only used these candidates at test time to select between.
Why are you providing candidates at all? That seems to complicate the whole system.
Yeah, I mean, obviously this data set can be used without candidates. That is true, yeah. I mean, yeah, I think, I'm not quite sure exactly why the decision was to provide candidates. I mean, okay, so, yeah, it might be that, you know, the average score might be something like 20% if you didn't provide candidates, or a very low number. In this case, I guess it just keeps it open to a wider range of models which can somehow score these and rank them, versus a model which really needs to make a choice from its whole vocabulary. That can often be really expensive and maybe not the sort of type of model that we want to. It also, in a way, yeah. Yeah, I agree that we could have done it without the candidates.
You're describing it as if this is someone else's data set, but you made this data set, right?
Yeah.
So
Well, I made it in collaboration.
The candidates
Yeah. That was my. Yeah, I suppose it was. We just. I can't remember the moment where we sort of agreed to put the candidates in. But you're absolutely right. Yeah, it was put together with me and collaborators. Yeah, I mean, it could be used without candidates, but I mean, one thing that we wanted to avoid was that you could only evaluate models based on complexity. So we wanted to have models where they could get a sort of numeric score. If you require models to give a probability to the right answer or something like that, then that obviously restricts the class of models that could potentially attempt the task. So that's one thing. Anyway, the interesting thing was that we found in this, we didn't try many different, so it's quite hard to optimize this network, and I was only doing this work for a short amount of time, so I didn't try many different representational forms, but one interesting thing, and the final thing, I guess, was that in this model, we found that, sort of small subsentential chunks were by far the most informative way of representing the content in the memory. So if we tried to incorporate the whole sentence in a single representation, and then just have 20 memories of sentences, the model would sort of lose information in some way. It would get blurred. But when we had chunks of length 5, just windows moving across the memory, and then the model was allowed to select by looking at those, then it performed a lot better. So, yeah, that's the end of the talk. So, yeah, just to recap. The long-term goal would be to try and make models of language understanding closer to the scenario in which humans learn language. I've done a bit of work which is sort of a little bit of the way there in terms of improving the supervised learning part, the function approximation part, and making it a little bit more realistic. But I think going forward, what I'm interested in doing is combining such models with different frameworks for training, which allow the models to take different training examples and explore areas of training data and things like that in order to see different effects and hopefully improve technology. So, thank you.
Unfortunately, we're out of time, but Felix will be here for the rest of the day, so if there's anything you would want to follow up on, please get in touch with me. Thanks a lot.